Welcome back. In this video, we are going to solve problem 4-101 that is taken from chapter number 4, Axial Load, and book name is Mechanics of Materials by R.C. Hibbeler. So statement is the rigid lever arm is supported by two A36 steel wires having the same diameter of 4 millimeter. If force of 3 kilonewton is applied to the handle, determine the force developed in both wire and their corresponding elongation. Consider A36 steel as an elastic, perfectly plastic material. So you can see this is the handle where there is a 3 kilonewton load applied, and these are two steel wires of 4 millimeter diameter. So you have to find the forces in this wire as well as elongation. Now you can see due to this force there will be elongation in wire A, B and CD. So what we will do is that first step is that we will find these forces. So this handle tends to increase the length of this wire AB. As a result, this wire AB applied force that will act downward. So this, if we remove this force, this wire AB will exert a force downward. Let this force is FAB. Similarly, if you remove this wire CD, so this will also exert a vertical force FCD in downward direction. And this at point E there is a pin support. So as a result of this, if you remove this support, so there will be a horizontal reaction force which is equal to EX, and there will be a vertical reaction force which is represented as EY. Now we'll find this FA, B and FCD by using equation of equilibrium. So what are these equation of equilibrium? So first equation of equilibrium is that sum of all moments about point E is equal to 0, taking the counterclockwise movement as positive. So about point E, these two forces are passing through point E, so they are not producing movement. So only the movement which is producing the only forces which is producing about movement about point E is the first one is this P, and perpendicular distance is 450, and this is producing clockwise movement, so it will be negative. So I will write P, which is 3 kilonewtons, so 3000 multiplied by 450, and this is producing counterclockwise movement, so it is negative. The second movement is due to FCD, and perpendicular distance is this 150, and since this is producing counterclockwise movement, so it will be positive. So I will write plus FCD into 150, and the last force which is producing about movement about point E is FAB into perpendicular distance is 300, and this is also producing counterclockwise, so it will be positive. So I will write plus FAB into 300 is equal to the sum of all moments about point E will be equal to 0. So if you divide this equation by 150 on both sides, so you will get 2 times FAB plus FCD is equal to 9000. Let this is your equation number 1. Now we can see that due to this load of P, this wire AB and CD elongates. So as a result, let this point AB comes toward this. This will be new point A dash, and C will come toward this point, and let this point is C dash. So this change in length between A and A dash is del A, change in length of AB, and from A to C it is this one, del CD. Okay, so this will be a straight line at this point. Let me draw it again. It will be a straight line because we assume that this is linear elastically perfectly plastic material. So this is your point C. Okay, now what we will do is that we will perform another analysis, that is elastic analysis. Let me write it, elastic analysis, and we have assumed that these material wires are elastic perfectly plastic material. So you can see that there are two similar triangle. One is this one, clear, and another one is this one. So if we take the ratio of their side, for example, if I take change in length of AB divided by this total length, which is equal to 300 millimeter. So it will be del AB divided by 300 will be equal to del CD divided by 150. So from here, what I will get is that del AB, change in length of wire AB, will be equal to 300 divided by 150 multiplied by change in length of CD. And if you further simplify it, change in length of AB will be equal to 2 times change in length of CD. Now we know that change in length is equal to force FAB into length AB divided by A into E. Since area is same, because both have same diameter, so area will be same, and 2 multiplied by change in length of CD will be equal to FCD into LCD divided by A into E. So again, if you further simplify it, this A will cancel with this A, and material is same, A36 steel. So I will, and length are also same, so these will cancel. So we will get this FAB is equal to 2 times FCD. So this will be our equation number 2. Okay. Now what we are going to do is that we will find the normal stress in each wires. So how we'll find that? Let me write it. Normal stresses. But before normal stresses, what I will do is that if I solve this equation 1 and 2, solving equation 1 and 2 simultaneously, so put, or you can also put equation number 2 in equation number 1. So let's put it, FAB is 2 times FCD, so 2 multiplied by 2 FCD plus FCD is equal to 9,000. So when you solve this, you will get force in wire CD will be equal to 1800 Newton. So if you have this FCD, so put FCD in equation number 2. So you will get FAB is equal to 2 times FCD. So 2 multiplied by 1800 Newton will give you FAB. That will be equal to 3600 Newton. So these are the two forces in wire AB and CD. Now we will check stress in these wires. So normal stress in wire CD will be equal to FCD divided by area of CD. So FCD is 1800. The diameter of wire is given 4 millimeters. So area will be pi by 4. And 4 millimeter in meter is 0.004. Pi by 4 d square. So when you solve this, this will be equal to 143.24 megapascal. Since we are given the A36 material steel, so from property table, its value is 250 megapascal. So you can see that stress in CD is less than yield stress. This is 143.24 megapascal, which is less than 250 megapascal. So it means that the stress or force in wire is okay. Now we will find the stress in wire AB. So stress in wire AB is equal to force in AB divided by area of AB. So force is 3600 divided by area is pi by 4. Again, diameter is 0.004 square. So when you solve this, you will get stress will be equal to 286.48 megapascal. And you can see this is greater than yield stress, which is 250 megapascal. So it means that this is not good. So what we will do, why not good? Because it is given that material behave elastically perfectly plastic, and it is exceeding the yield stress. So what we do is that I will write it, since wire AB yields, so the elastic analysis is not valid, and the solution must be reworked. So how you will rework? So we will use that, we know that yield stress is equal to force into area. So from here, this force in AB will be equal to, we will calculate force based on yield stress so that it lies within the yielding range. So we will know that yield stress into this area of AB will give force. So yield stress is 250 megapascal. So 250 into 10 raised to the power 6 multiplied by area is pi by 4. Diameter is 0.004 square. So when you solve this, you will get FAB, and FAB will be 3141.59 Newton, or you can say that this FAB will be equal to 3.14 kilo Newton. Now you have this force clear, and what we will do is that we will put FAB is equal to 3.14 kilonewton in equation 1 or 2. So if I put it in equation number 2, so I will also get FCD will be equal to 2.72 kilonewton. Now again we will check the stresses. Clear? So for that I will calculate CD is equal to FCD divided by area of CD. So FCD, which was new calculated, was 2.72 kilonewton. So 2.72 into 10 raised to the power 3 divided by pi by 4 into 0.004 square. So when you solve this, you will get 216.20 megapascal. And now you can see this is less than yield stress, which is 250 megapascal. So it means that it is still okay. So answers that force in wire AB is equal to, and force in wire CD is equal to. So force in wire CD is 2.72 kilonewton, and force in wire AB is 3.14 kilonewton. So this is the answer of our first part. Now moving toward next part, that is determine the elongation. Determine elongation in both wire AB and CD. So how we will find this? We know that elongation, change in length of CD, is equal to FCD into LCD divided by A into E. So FCD is 2.72 into 10 raised to the power 3 multiplied by length of each wire is given as 300 millimeter. So I will multiply it with 0.3 meter divided by area, which is pi by 4 into 0.004 square multiplied by E, which is 200 gigapascal. You can check the property, 200 into 10 raised to the power When you solve this, it will give you 0.000324 meter. Or you can say change in length of wire CD will be equal to 0.324 millimeter. Now we'll find change in length of AB. So change in length of AB is equal to FAB into LAB divided by area of AB into E. Put the values. FAB is 3.14 into 10 raised to power 3 Newton. Length is same, which is 0.300 divided by same diameter because the diameter is same area because the diameter is same and same material. So modulus of elasticity is 200 gigapascal, which is 200 into 10 raised to power 9. So when you solve this, you will get 0.000649 meter, or you can say change in length of AB is equal to 0.649 millimeter. Also, you can solve this by using this equation as well. Let me show the equation here. This is the equation. You can also calculate it if you know delta CD. So we can also calculate delta AB is equal to 2 times delta CD. So 2 multiplied by delta CD is 0.324. So it will be again equal to 0.649 millimeter. So change in length of wire AB is equal to 0.649 millimeter and change in length of CD is 0.324 millimeter. And these are the answers of our second part. So this was all about this problem 4-101. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Also share my videos with your friends and help me in growing my channel further. Thank you for watching. Welcome back. Problem 4-99. This problem is taken from chapter number 4, Axial Loading, and book name is Mechanics of Material by R.C. Hibbeler. So statement is the rigid beam is supported by a pin at A and 2 steel wires having diameter of 4 millimeter. If yield stress for the wire is 530 megapascal and modulus of elasticity for steel wire is 200 gigapascal, determine the intensity of distributed load W that can be placed on the beam and will cause wire EB to yield. What is the displacement of point G for this case? For the calculation, assume the steel is elastic and perfectly plastic. So you can see this is the beam at point A, it is pin supported, and at point B and C there are 2 steel wires of 4 millimeter diameter that is supporting. There is a distributed load over whole length which is W. So you have to find this W as well as displacement of this point G due to this load. So you have to find this displacement. So let's start with the solution. So what will be the first step? The first step is that if you remove this pin support at point A, so you will be having a reaction force which is equal to RAY, and if you remove it, so there will be a horizontal reaction force RAX. Similarly, if you remove this wire BE, so there will be a vertical reaction of this wire EB on this beam which is FEB, and similarly for CD the vertical reaction force offered by this wire CD will be equal to FCD on the beam. So what we will do is that again you can see there is a distributed load. So this distributed load when converted into a point load, so it will be equal to W, the magnitude, into the length over which it acts. So 400 plus 250 plus 180 is 800 millimeter. So 800 millimeter is 0.8 meter, and the unit will be in Newton per meter. Okay. So what we will do is that we will apply equation of equilibrium, that sum of all moments about point A is equal to 0, and taking the counterclockwise moment as positive. So you can see the moment about point A, the first moment is due to this FEB, and perpendicular distance is this 0.4 meter, and this is producing counterclockwise, so it will be positive. So I will write FEB or FBE into 0.4. The second moment is due to this FCD, and perpendicular distance is now 0.65 meter, and this is also producing counterclockwise, so it will be positive. So I will write plus FCD into 0.65, and the last moment that is produced due to this W into 0.8, and perpendicular distance is 0.4, and this is producing clockwise, so it will be negative. So I will write minus 0.8 times W into the perpendicular distance is 0.4. So from here what we will get is that 0.4 times FBE plus 0.65 times FCD is equal to 0.32 W. Let this is your equation number 1. Now we cannot apply any other equilibrium equation because it will not give you our required answer. So what we will do is that we will perform plastic analysis of wires, steel wires. What do you mean by plastic analysis? That the force is producing yield, the force is yield stress, and it is deforming permanently. So what we will assume that both steel wires fail, both steel wires, okay, let me correct it. This is steel wires yields mean it is deforming permanently. So for that we have been given the yield stress is 350 megapascal. So yield is 350 megapascal, and we know that yield stress is equal to yield force divided by area. So for BE and CD steel wire, the yield forces will be F of BE is equal to F of CD. Because both have the same diameter, we will have this formula sigma y into its area. So you have sigma y, which is 350 megapascal. So 350, 530, sorry, this is not 350, this is 530. Correct it as well, 530. So 530 into 10 raised to power 6 multiply by area. Diameter is given as 4 millimeter or 0.04 meter. So it will be pi by 4 times 0.004 square. That will give you force in BE and force in CD. So when you calculate it, both these forces FBE is equal to FCD will be equal to 6.660 kilonewton. Now you have these forces. Let this is your equation number 2. So put value of FBE and FCD in equation number 1. So this is your equation number 1. You can see this is your equation number 1. So when you put it the value, so you will get this W. I am not going to put it because this is very easy step. So you will get 21.9 into 10 raised to power 3 Newton per meter. Or you can also convert it is equal to 29.1 kilonewton per meter. Now you have this value. So what we are going to do is that we will we will find the displacement of this point B. Clear? So how we will find this displacement? So let's see that. Let me write first displacement. So as wire EB or BE achieve yield stress, so corresponding yield strain will be this one, and we know that this will be equal to yield stress over modulus of elasticity. So you can just put the value. Yield strain is equal to 530 into 10 raised to power 6 divided by modulus of elasticity is given as 200 gigapascal. So 200 into 10 raised to power 9. So when you solve this, you will get this yield strain will be equal to 0.002650 millimeter per millimeter. Now we have this yield strain. So what we are going to do is that we will find the change in length of this wire BE. So we know that strain is equal to change in length or original length. So for BE wire, clear? So this yield strain in wire EB or BE will be equal to change in length of BE divided by original length of BE. Clear? So we will find change in length of BE, that will be equal to LBE multiplied by yield strain. So what is the length of BE? So let me check. You can see both have length of 800 millimeter, which is equal to 0.8. So 0.8 multiplied by yield strain, which is 0.002650. So when you solve this, you will get change in length of wire BE will be equal to 2.120 millimeter. Now we have these values. So again, you can see that initially this beam was like this, clear? And due to the loading, this is your point A, this is your point, let's say B, this was your point C, and this is your point G. So due to the loading, the beam will go like this. So this will be the change in length of BE, delta BE. This will be change in length of delta CD, and this will be the change in length of our delta G, displacement of point G. So we know that the distance between A and B was 400 millimeter, or which is 0.4 meter. This distance between B and C was 0.25 meter. And distance from C to G is 0.15 meter. Now, what we'll do is that you can see you have two similar triangles, three similar. One is this one, clear? The second one is this one, clear? So we will take this similar triangle. Let's say this is your 1 and this is your 2. So two similar triangle. The first one is triangle, right angle triangle AB1, and other is triangle AG2. So by taking the ratio of their sides, so if I take AG divided by G2, so if AG divided by G2, that will be equal to AB divided by B1. So what we will get is that AG is totally 0.8. Clear? So 0.8 divided by delta G. G2 is delta G. That will be equal to 0.4 divided by delta BE. Clear? So from here we will get delta G will be equal to 0.8 divided by 0.4 into delta BE. That is equal to 2 times delta BE. Now what we get is that delta G is equal to 2 times delta BE. So put the value 2 multiplied by delta B is 2.120 millimeter. So you will get delta G will be equal to 4.24 millimeter. And which is the answer of our this question. So this was all about problem 4-99, in which we have been asked to find the distributed load, clear, as well as the displacement of point G. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Also share my videos and help me in growing further. Thank you for watching. Welcome back. Problem 4-91. This problem is taken from chapter number 4, Axial Load, and book name is Mechanics of Material by R.C. Hibbeler. So statement is determine the maximum axial force P that can be applied to the bar. The bar is made from steel and has an allowable stress of 21 ksi. So you can see this is the bar where there is a P load is applied. Clear? There is a hole in this bar as well as fillet in this bar. All the dimensions are given. This height is 1.875, this fillet radius is 0.2, diameter of hole is 0.75, and this height is 1.25 inch, and the thickness is 0.125 inch. So you have to determine this load P that can be applied to this bar. So let's start with the solution. As you can see, there is a hole and fillet in this, so we will need stress concentration factor. For that, you can see this figure 4.23 and 4.24. We will using these terms. So we will find, you can see here, this is W, R, H and T, here W, T and 2R. So we'll find this W. So W from this figure, you can see W is 1.875 inch. Now what about R? R is fillet radius, so R is 0.25 inch. What about this H? So H is smaller thickness, you can see this is H, so height which is 1.25 inch. And one more thing is thickness is 0.125 inch. And what about 2R, which is diameter? So you can see 2R is 0.75 inch. So we know all these things. So we will starting from fillet. So I will write assume failure of fillet. Failure of fillet. So we will find the stress concentration factor. So for fillet, we will need figure 4-23. We will find the value of W by H here and R by H. So W by H, which is equal to 1.875 divided by 1.25, that will give you 1.5, and R by H will be equal to 0.25 divided by 1.25, that is equal to 0.2. Now R by H is 0.2, so starting from this point you have to draw vertical line, clear, and that will coincide or intersect with W by H is 1.5 curve. So you can see this is W by H 1.5 curve. So it is intersecting at this point. So if you draw horizontal line, so this will be 1.7. So we will get K is equal to 1.7. Now we know that maximum stress or allowable stress is equal to K into sigma average. So K is 1.7 and allowable stress is 21 ksi. Let me check it. It is 21 ksi. That is equal to sigma average. So 21 is equal to 1.7 and sigma average is equal to P divided by this cross-sectional area. So cross-sectional area at this fillet point will be this height, which is 1.25, and this thickness, which is 0.125. So I will write 1.25 multiplied by 0.125. So from here, this P will be equal to 1.25 multiplied by 0.125 multiplied by 21 divided by 1.7. And when you calculate, this P will be 1.875 kips. So that is the load that is applied on the fillet or a failure of fillet. Now we will assume, we will find this P by assuming failure of hole. Again, we will find stress concentration factor. For that, we will need 2R by W. So 2R by W, 2R is 0.75 and W is 1.875. 1.875. That will give you 0.40. So again, you can see 0.40 is this point. If you draw vertical line, it intersects this curve. And when at intersection point, draw a horizontal line, you will get K is 2.2. So K is equal to 2.2. Now we know that allowable stress is equal to stress concentration factor into sigma average. So again, this is 221, this is 2.2 into P divided by area. Clear? So 21 is equal to 2.2 multiplied by P. Now you can see for this hole, you can see there is a hole and there is axial loading. So area will be equal to this 1.875 minus diameter of hole into this thickness 0.125. That will give you this portion and this portion. Clear? Because in tension, this hole does not take any load. So we will write this P is divided by area. Area is 1.875 minus diameter of hole is 0.75 into thickness, which is 0.125. So again, if you calculate for P, P will be equal to 21 into 1.875 minus 0.75 into 0.125 divided by 2.2. And when you calculate it, this will give you 1.34 kip. That is the load due to the hole. Now you have one load is this one and another one is this one. So you have to choose P is equal to 1.34 kips that can be applied to this system without causing any damage to this bar. And that was all about this problem 4-91. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon for getting the upcoming videos, and also share my videos with your friends and help me in growing my channel further. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. In this video, we are going to solve problem 4-92 that is taken from chapter number 4, Axial Load, and book name is Mechanics of Material by R.C. Hibbeler. So statement is determine the maximum normal stress developed in the bar when it is subjected to a tension of 2 kips. So you can see this is the bar here and the P load, axial load is applied. The magnitude of this load is 2 kips and there is a hole and fillet in this bar. So due to this hole, there will be a stress concentration. There will be the maximum stresses in this region as well as in this region of the fillet. So we'll find this maximum normal stress that will be developed in this bar. So let's start with the solution. So we know that maximum stress is equal to stress concentration factor into sigma average. So we have fillet and hole. So what we are going to do, we will find K for fillet and K for hole. So first we will find at fillet. So before that, we have to write some values, like you can see in this figure. This is W, this is H, this is the radius of fillet, and this is 2R, which is diameter of hole, thickness T, and this is W. So what is W? So W is equal to, based on this is 1.875 inch. What is H? So H is 1.25. What is R, radius of fillet, which is 0.25. Clear? And from this we will find R by H and W by H value. Clear? So we will use figure 4-23 and that will W by H. So W is 1.875 divided by H is 1.25, which will give you 1.5. And R by H. So R is 0.25 and H is 1.25. That will give you 0.2. So R by H is 0.2, which is this point. If you draw a vertical line from 0.2, that it will intersect the curves. So we will search for W by H 1.5. So this is W by H 1.5. So this is the curve. So you can see this is meeting at this point. So if at this point we will draw a horizontal line, that will give you the value of K, which is K is equal to 1.7. Clear? Now we have K. So we know that maximum stress is equal to K into sigma average. So K is 1.7 and sigma average is equal to P divided by A. So P is 2 kips. So 2 divided by the area over which it acts. So this is the area. So height is 1.25 and thickness is 0.125. So 1.25 is height and 0.125 is thickness. Clear? Okay. Now when you solve this, so you will get the maximum stress at fillet, which is equal to 22.4 KSI. Okay. We will now move toward for hole. So at hole, we will need one thing, which is 2R by W. So 2R by W. So 2R is diameter of hole, which is 0.75, and W is this height here, which is this one. and this is 1.875. So 1.875, that will give you 0.40. So at value of 0.40, draw a vertical line that will intersect this curve, and at point of intersection draw a horizontal line, so you will get the value of k, which is 2.2. So k is equal to 2.2. Now we'll find the maximum stress for this hole, that is equal to k into sigma average. So k is 2.2 and sigma average is load divided by area. So load is 2 psi divided by area. So you can see there is a hole. So this hole is not offering any force. So only the portion which will take this force will be this and this. How we'll find this? So if you take 1.875 minus this diameter of hole into thickness, which is 0.125, that will give you the area, because in tension hole does not play any role. So I will write 2 divided by 1.875 minus diameter of hole, which is 0.75, into thickness 0.125. Clear? And when you solve this, you will get the maximum stress or stress concentration near hole, which is 31.3 ksi. So now you have two value, one is this one and another one is this one, and in question we have been asked to determine the maximum normal stress developed in the bar. So the answer will be maximum stress, that will be 31.3 ksi, and which is the answer of our this question. And that was all about this simple problem 4-92. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it, and don't forget to press the bell icon so that you can get notification about my latest videos. Also share my channel with your friends and help me in growing further. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. In this video, we are going to solve problem 4-93, that is taken from chapter number 4, Axial Load, and book name is Mechanics of Material by R.C. Hibbeler. So statement is determine the maximum normal stress developed in the bar when it is subjected to tension of 8 kilonewton. So this is the bar, you can see, which is subjected to axial load of 8 kilonewton. There is a hole in this bar as well as in fillet. So due to this hole and this fillet, there will be a maximum stress at this portion, which is called stress concentration. So we have to determine that maximum normal stress developed in this load. So let's start with the solution. So we know that maximum stress is equal to K into sigma average, where K is known as stress concentration factor. And we will find this K for fillet as well as for hole. So starting from fillet, so at fillet, we will find this K. But before finding this K, we will find some values, which is R by H and W by H. So we will find what is W, what is R, what is H for this shape that is given in the rod. So you can see W is this one, which is the height, and that is 60 millimeter. So 60 millimeter. R is the radius of fillet. You can see R is this one. So that is 15 millimeter. And H is this height, which you can see that is given as this height here, and this is 30 millimeter. So 30 millimeter. Now you have this value, you have to find, use figure 4-23, that is for fillet, and you have to find R by H and W by H. So first we will find R by H and W by H. So what is R by H? R is 15 and H is 30, that will give you 0.5, and W by H is 60 divided by 30, that will give you 2. Now R by H is 0.5, which you can see is this point. If you draw a vertical line from this point, that will intersect these curves above. And we will locate W by 2. So W by H is 2. So you can see this is the curve which is intersecting at this point. So if you draw a horizontal line, so you will get the value of K is 1.4. You can see this on y-axis, this is K. So I will write K is equal to 1.4. Now you will use this equation, sigma max is equal to K into sigma average. So what is K? K is 1.4, and sigma average is load per unit area. So this is the load and this is the cross-sectional area. So load is 8 kilonewton. So I will write 8 multiplied by 10 raised to power 3 divided by area. So this height is 30 millimeter, which in meter is 0.03 meter, and thickness is 5 millimeter, which is 0.005 meter. So I will write 0.03 multiplied by 0.005, clear? And when you solve this, you will get maximum stress due to this fillets comes out to be 74.7 megapascal. Now we will move toward hole and we will find K for hole. So at hole. So for hole we will need 2R by W. So what is 2R and what is W? So 2R, you can see this is the hole of diameter, which is 12 millimeter. So 12 divided by W is this height of maximum portion which is carrying this hole, that is 60. So 12 divided by 60 will give you 0.2. Clear? Now look at the 0.2. So 0.2 is this point. So from this point, draw vertical line. It will intersect this curve. So from point of intersection, you can just move it over here. So this is 2.4, 2.45. This is 2.5. Clear? So this value is 2.45. So K will be equal to 2.45. Now for hole, we know that maximum stress is equal to stress concentration factor into sigma average. So 2.45 into load, which is 8 into 10 raised to power axial load, 8 into 10 raised to power 3 Newton. And you can see that this bar is carrying holes. So for area, we will take 60, which is 0.06 meter minus diameter of hole, which is 0.12 into the thickness, which is 0.005. Clear? Because this hole is not offering any resistance to this axial loading. So thereby we subtract it from the net cross-sectional area. So I will write 0.06 minus the diameter of hole, which is 0.012 into thickness is 0.005. And when you calculate it, you will get maximum stress in hole or on the side of hole will be equal to 81.7 megapascal. Now this is the stress, maximum stress that is generated due to hole, and this is the maximum stress generated due to this fillet. So in question we have been asked, determine the maximum normal stress developed in the bar. So among these two or between these two, we will choose the maximum stress generated in bar is 81.7 megapascal, and that is the answer of our this question. And that was all about this problem 4-93. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel are requested to subscribe my channel and hit the bell icon so that you can get notification about my latest videos. Also share my videos with your friends and help me in growing my channel further. And if you have any question, you can ask me in comment section. Thank you for watching and supporting me. Welcome back. In this video, we are going to solve problem 4-94 that is taken from chapter number 4, Axial Load, and book name is Mechanics of Material by R.C. Hibbeler. So statement is the resulting stress distribution along section AB for the bar is shown. From this distribution, determine the approximate resultant axial force P applied to the bar. Also, what is the stress concentration factor for this geometry? So you can see this is a bar having fillet, clear, and at section AB, the stress distribution is shown like that, clear, and there is a P load applied to this bar. So you can see the highest intensity is 12 ksi, and the intensity of each of this segment is 3 ksi. So there are 4 segments, and if we count it, so there are 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 approximately square bar. The thickness of this bar is 0.5 inch. So let's start with the solution. So as we know that this P load is equal to integral of stress into dA. So what does it mean? It means that volume under curve. So where is the curve? So you can see this is the curve, clear? So volume of this curve will be like this one. Okay, so how we'll find this? So let's start solving this problem. So as we know that I have already discussed that number of square in this volume is equal to 10. Let me count it again. So you can see 1 square, 2 and 3 plus 4, 5, 6, 7, 8, 9 and 10. So approximately there are 10 square. So we know that P will be equal to, you can see the intensity of 1 is 3, one of the square side is 3 ksi. So 3 multiplied by the area, what is the area? So 1 is the height of this and 0.5 is the thickness. So 3 into 1 into 0.5. So there are 10 squares, so I will multiply it with 10. So it will give you the P load, which is the volume under the curve. And when you calculate it, it will be equal to 15 kips. So I will write P will be equal to 15 kips, which is the answer of our first part. Clear? Now we'll find the stress concentration factor. I will write it stress concentration factor K. So we know that due to this fillet, there will be a maximum stress at this fillet portion, clear, and minimum stress will be at the middle. So what we will going to do is that we will find this stress concentration factor. So we know that this maximum stress will be equal to stress concentration factor into sigma average. So how you will find sigma average? So sigma average is equal to P divided by A. Now what is P? So P is 15 kips. So 15 kip multiply by what is the area of this portion? So this is thickness 0.5 and total height is 4 inch. So this will be the cross-sectional area over which this P act. So P divided by 4 inch multiply by 0.5 inch, and when you calculate it, it will be 7.5 KSI. Okay. So from here, sigma average is equal to 7.5 KSI. So what we are going to do is that we will find this K, clear? So how we'll find this K? You will need average maximum stress. So maximum stress can be taken from curve, and that maximum stress is 12 KSI. So sigma max is equal to 12 KSI. So we know that maximum stress is equal to K into sigma average. So from here, this K will be equal to sigma max divided by sigma average. So put the value, sigma max is 12 KSI and sigma average is 7.5 KSI, which will give you 1.60. So the stress concentration factor is 1.60 required stress concentration factor for this bar, which is the answer of our this question. And that was all about this problem 4-94. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. Also share my videos with your friends and help them in learning process. And I am very thankful to you people for supporting me throughout my this journey on YouTube channel. Thank you. Welcome back. In this video, we are going to solve problem 4-95 that is taken from chapter number 4, Axial Load, and book name is Mechanics of Material by R.C. Hibbeler. So statement is the 10 millimeter diameter shank of steel bolt has a bronze sleeve bonded to it. The outer diameter of this sleeve is 20 millimeter. If yield strength stress for steel is 640 megapascal and for the bronze, this is 520 megapascal, determine the largest possible value of P that can be applied to the bolt. Assume the material is to be perfectly plastic. Elasticity of steel is 200 gigapascal and for bronze it is 100 megapascal. So you can see this is bolt, clear, having diameter 10 millimeter, and that is sleeve, bronze sleeve that is made up of bronze that is bonded to it, having outer diameter 20 millimeter. So diameter of bolt is 10 millimeter, in meter it is 0.01. The outer diameter of sleeve is 20 millimeter, which is 0.02 meter, and inner diameter is same as for bolt. Sleeve is made up of bronze. Yield stress for steel is 640, while yield stress for bronze is 520 megapascal, and their modulus of elasticities are mentioned. So you have to determine the largest possible value of P that can be applied to the bolt. And how we will find this? So let's start with the solution. So first step is that what if I cut the bolt over here or any length and draw the free body diagram. So let me draw it, that this is the head of this bolt, clear, and this is the sleeve. This is the sleeve. Okay, and this is the dotted line is the diameter of this bolt. So when I cut it, so you can see at the top we have a load P, which we are going to find. Clear? And you can see that this load is taken, some of this portion of this load is taken by this bolt, which is represented as PB. Clear? PB. And some of this load is taken by the shank, so that is PS. So total load P will be equal to PB plus PS. So how we'll find this? By using equation of equilibrium, that sum of all forces along y direction must be equal to 0 and force upward is taken as positive. So I can write P minus PB minus PS is equal to 0, or you can also write it that P is equal to PB plus PS. Clear? Now how we'll find this PB and PS, and we are interested to find out the largest load. So I will write a statement that the largest possible P can be applied when you consider when P causes both bolt and sleeve to yield. That is the maximum load P that can be applied. So how we'll find this PB? So we know that yield stress for the steel is equal to load taken by the bolt divided by area of bolt. Clear? So from here, this PB will be equal to yield stress for this steel multiplied by area of bolt. So you can see 640 megapascal is the yield stress for steel. So 640 multiplied by 10 will be in pascal multiplied by area of bolt. Diameter is given as 10 millimeter, which is 0.01 millimeter. So area of bolt is pi by 4 d square, db square. So db is 0.01 square. That will give you PB. This PB will be the load that will cause the yielding in steel rod or steel bolt. And when you calculate it, you will get 50.265 kilo Newton. Now we'll find the PS of sleeve. So we have yield strength for bronze that will be equal to P of brass. This is P of steel, PS. This is PS because this is the load taken by the steel. Now P of brass divided by area of brass, and similarly this will be AS, area of steel. So kindly make this correction. Okay, so from here, load taken by brass sleeve will be equal to yield strength of this brass multiplied by area of this brass. So the brass yield stress is 520 megapascal, so 520 multiplied by 10 to the power 6, and this sleeve having outer and inner diameter, so it will be equal to pi by 4. Outer diameter is 0.02 square minus inner diameter is 0.01, and the formula is pi by 4 d outer square minus d inner square. Now when you calculate it, the load taken by this brass sleeve will be equal to 122.52 kilo Newton. As we know that we are interested to find of P, and we know that P is equal to PB plus P of steel, which we have written over here. Clear? So put the value 50.265 is the value of steel, load taken by this steel rod or bolt, plus P bronze, which is 122.52 kilonewton. So when you add them both, so you will get 173 kilonewton. So this is the amount of the maximum amount of load P that can be applied on this steel bolt having bronze sleeve bonded to it. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon for getting the upcoming videos. And if you have any question, you can ask me in comment section. Thank you for watching and keep supporting me like this. Welcome back. Problem 4-96. This problem is taken from chapter number 4, Axial Load, and book name is Mechanics of Material by R.C. Hibbeler. So statement is the 10 millimeter diameter shank of steel bolt has a bronze sleeve bonded to it. The outer diameter of this sleeve is 20 millimeter. If the yield stress for the steel is 640 megapascal and for the bronze is 520 megapascal, determine the magnitude of largest elastic load P that can be applied to the assembly. E of steel is 200 gigapascal while E of bronze is 100 gigapascal. So you can see this is the steel bolt, clear, having diameter 10 millimeter, and this is the sleeve that is bounded to this bolt having outer diameter 20 millimeter and inner diameter is 10, clear, and their P load is applied on it. So all the values are given. This is the diameter of bolt, This outer diameter of sleeve, inner diameter of sleeve is made up of bronze. Yield stress for steel is 640 megapascal, and for bronze is 520 megapascal, and their modulus of elasticities are mentioned. So you have to determine the largest value of P that can be applied to the assembly. So this is not bolt, this is for the assembly. So let's start with the solution. So what will be the first step is that if you cut the bolt at any section and draw the free body diagram, so it will be like this. And first I will draw this bolt here. This is the sleeves. These two are sleeves. And this is dotted line is the diameter. This is the bolt section. Clear? So you can see the bolt is applied by a load of P that is upward. So when you cut it, so some portion of this load will be taken by the bolt. This is PB, the load taken by the bolt, and some of the portion of load is taken by this sleeve, which is represented as PS. So we will apply the equation of equilibrium that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So from here we know that P is upward minus PB, which is downward, minus PS is equal to 0. So either we can write it P is equal to PB minus plus PS, or again you can also leave it like this. It's depend on you. So this is your equation number 1. Now you can see that this sleeve is bounded with this bolt. Clear? So due to this load there will be elongation in sleeve and bolt, and both elongation will be same because due to bonded sleeve we have change in length of bolt is equal to change in length of sleeve. So we know that this change in length of bolt is equal to PB into LB, length of bolt divided by area of bolt, into E of steel. Clear? Because the bolt is made up of steel. And change of length of sleeve is equal to P of sleeve into length of sleeve divided by area of sleeve into E of bronze, because this sleeve is made up of bronze. So put the value. PB is not known. Clear? So PB, LB and LS. LB is equal to LS, both of the same length, that is equal to L. Therefore, these two value will cut. So PB divided by area of bolt, so pi by 4 d square, diameter of bolt is 0.01 meter, so it will be in square, d square into E of steel. E of steel is 200 gigapascal, 200 into 10 to the power 9 is equal to P of steel divided by area of steel, which is pi by 4 d outer square minus d inner square. So d outer is 0.02 square minus d inner is 0.01 and its square, multiply by E of bronze, which is 100 gigapascal, 100 into 10 to the power 9. So when you solve this for PB, so PB will be equal to 0.667 P of sleeve. Clear? Okay. Now what we will do is that we will first assume, we will categorize by using two assumptions. First assumption is assume yielding of bolt. Yield of bolt. So we know that yield stress of this steel is equal to P of bolt divided by area of bolt. So from here, what you will get is that PB is equal to yield stress of steel into area of bolt. So yield stress is given as 640 megapascal. So 640 into 10 to the power 6 multiplied by pi by 4. Diameter of bolt is 0.01 and its square. Clear? That will give you PB. So when you get PB, PB will be 50.265 kilonewton. Now you have this value of PB. So what you can do is that this was your equation number 2. So put PB in equation 2. You will get PS, and that PS will be 75.400 kilonewton. Now you have PB and PS. So what you can do is that put PB and PS in equation number 1. So you will get this P, and this P comes out to be 126 kilonewton. So this is the load that can be applied to this assembly, assuming the yielding of bolt. Now what we will do is that we will apply second criteria, and the second criteria is assuming yield of sleeve. So we know that yield strength of this bronze is equal to P sleeve divided by area of sleeve. So from here, load taken by the sleeve will be equal to yield of bronze, because this sleeve is made up of bronze, into area of sleeve. So yield stress is 520 megapascal. So 520 into 10 to the power 6 multiplied by area, which is pi by 4 d outer square minus d inner square. So d outer is 0.02 square minus d inner is 0.01 square. Okay. So when you solve this, you will get P of steel will be equal to P of sleeve, not steel. There is a little bit confusion in this. This P of sleeve will be 122.52 kilonewton. Now you have this value. So put PS in equation number 2. So you will get PB, and that PB will be equal to 122 PB comes out to be 81.68 kilonewton. Okay. Now you have PB and PS value. So put PB and PS in equation number 1, which is this one. This one. So when you put it, you will get P will be equal to 204.20 kilonewton. Now this is the load that is due to assuming the yielding of sleeve. Clear? So one P is this one, another one is P this one. So what we will do is that we will choose one which will be safer. So P is equal to 126 kilonewton load that can be applied to this assembly, because this is the largest elastic load that can be applied to this system. And that was all about this problem 4-96. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it, and don't forget to hit the bell icon for getting the new upcoming videos. If you have any question, you can ask me in comment section. Also share my videos with your friends and help them in learning process. Thank you. Welcome back. In this video, we are going to solve problem 4-97 that is taken from chapter number 4, Axial Load, and book name is Mechanics of Material by R.C. Hibbeler. So statement is the weight is suspended from steel and aluminum wires, each having the same initial length of 3 meter and cross-sectional area of 4 square millimeter. If the material can be assumed to be elastic, perfectly plastic, with yield stress of steel is 120 megapascal and for aluminum 70 megapascal. Determine the force in each wire if part A is weight is 600 Newton and if weight is changed to 720 Newton. Aluminum modulus of elasticity is 70 gigapascal and for steel it is 200 gigapascal. So let's start with the solution. So what we will do is that if you cut this wire over here and draw the free body diagram, so I will draw this free body diagram, that this is the weight, clear, and this is the hook. Okay, so this is the load taken by aluminum, which is FAL, and this is the load taken by this steel wire, which is F of steel, and this is the weight which is acting downward, W. So what we will do is that we will apply equation of equilibrium, that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So F of steel plus F of aluminum minus W is equal to 0. So from here, that this is your equation number 1. Now what we will do is that we will assume, and it is also given that assume both wires behave elastically. So what does it mean? That it means that change in length of aluminum will be equal to change in length of steel rod. And we know that this change in length of aluminum is equal to F aluminum into length of aluminum, which is equal to, both lengths are same, which is equal to L. So I will write L divided by area into E. E is 70 gigapascal for aluminum. It is 70. Clear? And both areas are also same. So that is A will be same. So I will write it, area of steel is equal to area of aluminum is equal to A. They both are same. Similarly, E, change in length of steel is F of steel into length divided by area of steel into modulus of elasticity, which is 200. So if you solve for force in aluminum wire, so F aluminum will be equal to 0.35 F time steel. Now we will solve it for part 1. Let this is your equation number 2. So for A, when W is equal to 600 Newton. So put equation 2 in equation 1 and value of W. So let me put it, F of steel is equal, F of steel plus F of aluminum is equal to 0.35 times F of steel minus 600 is equal to 0. So from here, you will get F of steel will be equal to 444.4 Newton. Or you can say this is 444 Newton. Clear? So put F of steel in equation number 2. So what you will get is that F of aluminum is equal to 0.35 times F of steel. So 0.35 multiplied by F of steel is 444 Newton. So you will get force in aluminum wire, which is equal to 156 Newton. Now you have both these forces. So what we will do is that we will find stress in aluminum wire, which is equal to F of aluminum divided by area of aluminum. So F of aluminum is 156 divided by area is given as 4 square millimeter. So area is equal to 4 square millimeter. So in meter, it is equal to 4 into 10 to the power minus 6 square meter. So I will put the value 4 into 10 to the power minus 6. So when you solve this, you will get 38.88 megapascal. This is stress in aluminum. You can see that yield stress of aluminum is 70 megapascal, and this stress is less than yield stress of aluminum, which is 70 megapascal. So it means that this is okay. This wire is okay. Now for steel, it will be equal to F of steel divided by area. So F of steel is how much? F of steel is, you can see, where is F of steel? F of steel is 444. 444 divided by 4 into 10 to the power minus 6, and when you calculate it will be 111.11 megapascal, and this is also less than yield strength of steel, which is given as 120 megapascal. So it means that this wire is also okay. Now what we will do is that we will solve for part 2 and for B when W is equal to 720 Newton. So put value of equation 2 and W is equal to 720 in equation 1. Where is equation 1? So this is equation 1. So F of steel will be equal to F of steel plus F of aluminum. So F of aluminum is 0.35 times F of steel minus 720 is equal to 0. So when you calculate it, you will get F of steel will be equal to 5333.3 Newton. Now put value of F of steel in equation 2. So you will get F of aluminum will be equal to 186.67 Newton. Clear? So what we will do is that again we will solve average normal stress in aluminum wire, which is equal to F of aluminum divided by A. So F of aluminum is 186.67 divided by area, which is 4 into 10 to the power minus 6. So you will get 46.67 megapascal, which is less than yield strength of aluminum, that is 70 megapascal. So it means that the force in this wire, aluminum wire of 186 is okay. Now for steel, this is equal to F of steel divided by area. So F of steel is 5333.33 divided by area, which is 4 into 10 to the power minus 6. And when you calculate, it will be 133.3 megapascal. And you can see this is greater than yield strength of steel, which is 120 megapascal. So what does it mean? That it means that steel wires yields. Clear? So what we will do, hence we will find the force in steel wire by using yield strength of steel. So force in steel wire is equal to yield strength of steel wire into area of steel wire. So this is 120 into 10 to the power 6 is yield stress of steel wire into area 4 into 10 to the power minus 6. So from here you will get force in steel wires will be equal to 480 Newton. Clear? Now we have this 480 Newton. So put F of steel is equal to 480 Newton in equation number 1. Equation number 1, which is this one. You can see this is the equation. Clear? And W is also 700 Newton. So you will get F of aluminum. So F of aluminum, you will get it will be equal to 240 Newton. Now, what we will do is that we have the yield stress in steel wire will be 120 megapascal. So force in aluminum wire is 240. So stress in aluminum wire will be equal to 240 divided by 4 into 10 to the power minus 6. And that will be 60 megapascal, which you can see less than the yield strength of aluminum wire. Clear? So what we will conclude is that we will conclude that based on your first weight of 600 Newton, you will have force in steel wire is 444 and force in aluminum is 156 Newton. While based on 700 Newton load, your force in steel wire is 480 Newton and force in aluminum wire is 240 Newton. And this was all about problem 4-97. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Also share my videos with your friends and help me in growing my channel further. Thank you for watching and your support. Welcome back. Problem 4-98. This problem is taken from chapter number 4, Axial Load, and book name is Mechanics of Material by R.C. Hibbeler. So statement is the bar has a cross-sectional area of 0.5 square inch and is made of material that has stress strain diagram that can be approximated by two line segments shown. Determine the elongation of bar due to the applied loading. So you can see this is the bar where this at point C we have 5 kips load and at point B we have 8 kips load. And the stress strain diagram for this bar is given by two lines. So you have to determine the total elongation of this bar AC. So let's start with the solution. So as we know that total elongation in this bar will be equal to elongation in bar AB plus elongation in bar BC. Here you can see that we know that elongation or change in length is equal to PL divided by AE. So we do not know the material. It is not given. So we cannot apply this equation. So what we will do is that in this video, I will show you how to solve this problem. So first step is that what we will do is that if you cut this member BC, so for member BC or for segment BC. What if I cut it and draw the free body diagram? So this is member BC. At this we have 5 kips load, clear? And in order to balance it, we will having this load, that this is PBC. So by using equation of equilibrium, that sum of all forces along x direction must be equal to 0 and force toward right side is taken as positive. So PBC, which will be minus plus 5, is equal to 0. So from here we will get this PBC will be equal to 5 kip. Now you have this PBC. So what we will do is that we will find the average normal stress. So average normal stress in segment BC will be sigma BC is equal to PBC divided by area. So you have PBC is 5 and area of this bar is given as 0.5. So when you solve this, you will get 10 KSI. So stress in segment BC is equal to 10 KSI. Now what we will do is that we will find the stress in for segment AB. So I will write for segment AB. So what if I cut the segment AB and draw the free body diagram over here? So it will be like this. This is your point C where you have 5 kips load, clear? And this is your point B where you have a load of 8 kips. So in order to balance it, we should have a force toward left side, and this force will be equal to PAB. So how you will find PAB? By using the same equation, sum of all forces along x direction must be equal to 0 and force toward right side is taken as positive. So PAB is in negative direction. So PAB plus 8 plus 5 is equal to 0. So from here you will get this PAB will be equal to 13 kip. Now you have this PAB. So what we are going to do is that we will find the average normal stress for PAB, that will be equal to PAB divided by area. So PAB is 13 divided by 0.5 and that will give you 26 KSI. So average normal stress in portion AB is 26 KSI. Okay, now we'll find the strain in segment BC. So how we'll find the strain in segment BC? So if you see that stress, we know that stress is equal to strain into E, clear? And E is equal to stress divided by strain. So we will take this ratio, stress divided by strain. So for segment BC, we have strain sigma BC. If you take it and divide by, let me write it, we know that stress over strain. So for sigma BC over epsilon BC, if I take it, this will be equal to 10 divided by epsilon BC. And what if I take the ratio at this point? This is 20 sigma, and over for this 20 sigma we have epsilon is 0.01. So we will take the ratio that sigma 10 divided by epsilon BC will be equal to 20 divided by 0.001. Let me explain again. You can see that this sigma BC is 10 KSI, that will be in this line. So if I take like this is 10, clear? So at 10 we will have some strain. So if the ratio of stress over strain at this point to the ratio of stress over strain to this point will be same. So what I have written is 10 divided by epsilon BC is equal to 20 divided by 0.001. So from here we will get strain BC will be equal to 20 divided by 0.001. Strain will be equal to, sorry, let me correct it. It will be equal to 0.001 multiplied by 10 divided by 20. And when you solve this, you will get strain in BC will be equal to 0.00050. And it will be either unitless or inch by inch. So this is strain in BC. Now what we will do is that we will find the strain for portion AB. So what we will do is that you can see the stress is sigma AB, clear? So here, this is in this line. You can see this will be in, let me choose another, this will lie in another line, in this line. So you can see 26, so 26 will be either somewhere here, let this is 26. So if I take horizontal line, so at this point we will have strain will be epsilon AB. So what if I take the difference of these two stresses? For example, 26 minus 20 divided by epsilon AB minus 0.01. Let me write it. So you can see 26 minus 20 over epsilon AB minus 0.01. That will be equal to this 40 minus 20, this 20, clear? So 40 minus 20 divided by, at 40 we have strain 0.021 and at 20 we have 0.01. So 0.021 minus 0.001. So from here, when you solve this, you will get strain in portion AB will be equal to 0.0070 inch by inch. or it will be a dimensionless quantity. Now you have strain in BC and you have strain in AB. So we will move toward elongation. I will write elongation. So we know that change in length is equal to, strain is equal to change in length divided by original length. So for segment BC, this change in length will be equal to, change in length of BC will be equal to strain in BC into length of BC. So what is strain in BC? You can see that is this one, 0.00050 multiplied by length of BC. So length of BC is 2 feet. So 2 and 1, we convert this feet into inch. So I will multiply it with 12. Okay, so when you multiply, it will give you 0.0120 inch. So this will be the change in length of BC, 0.0120 inch. Similarly, we will find for segment AB, So change in length of AB is equal to strain in AB multiplied by length of AB. So strain in AB is 0.0070 multiplied by length of AB. You can see this is 5 feet. So 5, and when you convert this feet into inch, so because 1 inch is equal to 1 feet is equal to 12 inch. So when you multiply it, you will get 0.420 inch. This will be change in length in AB. Now total elongation or total change in length will be equal to change in length AB plus change in length BC. So 0.420 is change in length of AB plus 0.0120 in length BC. So when you calculate it, you will get total change in length will be equal to 0.3432 inch. So due to the applied loading, total change in length is 0.432 inch. And that was all about this problem 4-98. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Also share my videos with your friends and help me in growing my channel further. Thank you for watching.